All right, everybody, I think we're going to get started with the 2 o'clock session here. My name is Kurt Kennedy. I am a pediatric intensivist from Texas Children's Hospital in Houston, Texas. I also did some training in informatics beyond that. And I'd like to thank Anthony for inviting me up here to speak again this year. I'd like to thank Leo and Kevin for being up on the stage with me as well to talk to you today about cloud computing, big data, and cybersecurity. So Kevin is, actually Leo's going to go first, and he's going to talk to us about the Mimic database. Kevin's going to talk about blockchain, and what I'm going to do before either of those is provide kind of a Texan's viewpoint, which is a little bit more basement level understanding of big data, cloud computing, and talk to you a little bit more in metaphor for those of you that may not understand all the code and specific high-level stuff that we're talking about today. Just a little bit about who I am. My favorite picture in the world is this one here in the top left, and I really do wish that were me because that is what is in my heart. They didn't have that kind of computer when I was that age, but tip of the hat to whoever took that picture because they've really touched me there. I come from Texas. That is not a picture of me as well, but that's what I want y'all to think of me doing because that would also be something that I'd be very happy doing is just hanging out there with the horse, playing with the computer. That's how we roll in Texas. Far right-hand picture actually is me. That's just to prove to you that I've been doing computers for quite a long time. Bottom left is Texas Children's Hospital where I work, and then the bottom middle picture is me with my lovely wife and 2 children. So the first thing we're going to cover is big data and what is it. And I told you that I was going to be talking a little bit more in metaphor today. So in my institution, probably in many of y'all's institution, this is us here, the little baby with the dump truck playing in the sandbox. And it's not really a big data application. You've just got a job to do. You know, you're going to fill that dump truck up and you're going to do something useful with it. But then you go out there and you see Dad's truck and you're like, wow, that's big data. I wish I had the capability of using that thing. I could really do some damage if I could get up there in that truck and do something with it. But I'm not big enough. I don't have the skills to use that yet, so I just have to kind of wait for it. All right, so I grow up a little bit and, you know, I've moved up into my own truck that I can drive around. I can start to get dirty in the mud a little bit and play a little bit harder. So that's great. But then the trucks are getting bigger. Right? We're growing at this exponential rate here. Now I've got an adult that's looking up at their own big truck there saying, wow, that would be really cool if I could get in there and drive that. But, I mean, what's somebody like that actually going to do with a big truck like that? Probably not a lot. I mean, it'd be kind of fun to just drive it around the parking lot, but in terms of functional work, you're not going to do much. So at the end of the day, what it is, you know, I'm this little kid sitting by this rust bucket of a truck. I mean, it's big and huge. But it might as well not even be functioning because there's not a lot I can do with it. And over here, this is what I really think big data is. It's a big dump truck that can do a lot of good work, but it takes a team of people to do that. You've got to have people that load it, unload it, that know where that stuff's going to go once you've actually turned a work product over. And it's kind of this infrastructure of a team. So that's kind of the take-home message I'd want to get from that. I'd say just from a simple Texans perspective, big data is data that's too big or complex for you to work on. You need better expertise, tools, teams, something that, you know, would allow you to actually work with that data. From a comparative perspective, there's probably some analogy here that involves size and trucks, comparisons, maybe mixed in with some envy and insecurity. If anybody can help me out with what that analogy might be, you're welcome to it, but I'm having a hard time myself. As a concept, I want to point out something here. So we've talked about big data, and what is that? Well, the Large Hadron Collider has 150 million sensors that send over 40 million times a second information in here. 5 data points out of 1 million are actually collected for analysis. And that would be basically like studying San Francisco, all the people in San Francisco by looking at a first grade classroom and saying, you know, what can I learn from that? It generates 25 petabytes of data every year and is processed by 170 computing centers in 42 countries. To me, that's really big data. I would argue that that project is working on a single patient. They've kind of got a vision about what they're doing. And I'm going to flip it around in healthcare and say that we've got over 1,000 times more data in the healthcare environment than what they're collecting there. We've got about 7 billion patients, not just the one that they're focused on. And the data that we've got is fragmented, our efforts are fragmented, and our total resources to work on that probably are about the same as what they're using. So that actually scares me a little bit in terms of, do we actually have any hope here in the first place? The next thing we're going to do is move over to the cloud and talk to it in metaphor a little bit. So in our institution, we've got a box that we put data into, and we've owned that box. We control it. It's on our property. And if we want to mess with it or have security with it, we've got a little padlock on it. We open it up. If we move it, we've got to get a truck in there to move it from one point to another. It's a lot of work. And I would argue is a fairly vulnerable thing for us to control this one little box. But if you put it in a system to where boxes are their business, then you basically inherit the infrastructure that supports all of that. So if you want to go get into the box, there's a process for doing that. And you don't have to spend all of your resources in an organization maintaining all of the things that are not inside the box. You can focus on the stuff that's inside the box rather than focusing on protecting the stuff that's around it. That may not be the best metaphor in the world, but that's the one I came up with. So from the standpoint of the cloud, I'd say that, number one, when you put it in there, it's still got your data, but you've also got this ever-expanding suite of tools that you're going to be able to use to work on the data. The other advantage to the cloud is that you're in there with a bunch of other boxes. So you've got other people's data that are in there in kind of a similar space, and that's where you start to have the ability to collaborate and turn, your, quote, big data project into a real big data project that's really applicable to more than just your particular infrastructure. And finally, we're going to talk about cybersecurity. When we talk about, hacks and cybersecurity, people think of this very glamorous and exciting pirates jousting around. I'm going to steal your gold. Arr! It's kind of an exciting topic to discuss, when in reality, you're standing there minding your own business, and you look down, and you've got all these fire ants on you. In Texas, this is what we actually do. We're standing around in the yard, and the next thing you know, you end up bitten by a bunch of ants, and it stings and it hurts when that happens. And when you talk about, well, what can we do about that? I would argue number one is, if you're going to be in the cloud and you're going to collaborate, once you de-identify the data, and that's what they did with Mimic, and Leo's going to talk about that, you're kind of done. You can actually open that data up to the world, and the security of it's not quite that important anymore. And then the other part of that is, if you're going to have your own container, then the resources that you're going to have to use to protect it are probably not going to be the best in class in the world. You're not in that ecosystem where that is their business, to deal with the security of those containers. So, from my point of view, it makes logical sense to kind of be one of many in the cloud, rather than kind of cowboying it all alone out there, controlling everything. Now, that being said, I do appreciate that there's drawbacks to both models, but I'm presenting the side. Okay, I'm going to close off with about 5 challenges. From a hospital's perspective, they're concerned about risk. If they're going to use resources, they want to know about return on investment. And then there's some degree of it's our data, it should be our glory. I would just argue that we need to kind of get over that. From the standpoint of a clinician, we're limited in time. I take care of patients in addition to doing all of the data things that I do. Many of them lack computer knowledge. Data scientists, a lot of those guys lack medical knowledge. So a tip of the hat to Randall and you other guys out there that bring data scientists into the clinic to actually see what's going on. The people that provide tools that say that they're doing AI, be transparent about what the limitations are. There's a lot of things up here where a lot of hype is given and promises made that aren't necessarily true. If we're really going to evolve, we've got to be transparent about what those limitations are. And finally, patience. This is the most important part. If you want to be part of your healthcare, you've got to advocate for yourself. You've got to jump up and scream and shout and say, give me my data, and make it available for good use. And with that, I'd like to thank you.
Hello. I couldn't help admiring Kurt's Texan boots. Actually, if you could see it more closely, it's awesome. I'm here to talk about Mimic, but I want to start off with a slide about cybersecurity. But before that, yes, Mimic. You've heard about this, so I'm going to actually skip this. But I want to mention that we have another open data that is available to investigators around the world. It's a subset of the Philips EICU database. They collect data from about 10% of the ICU beds from the United States. So that's 400 hospitals. It's the same resolution as Mimic, except that it doesn't have any waveforms, it doesn't have notes, and it doesn't have images as well. But this is 10 of the biggest security breaches in 2017, and now they're reporting about 3 security breaches per week. And you could see here that these are all related to healthcare. So 1 in 5 security breaches this year was actually related to healthcare data. And these are some of the things that we do at MIT to make sure that the Mimic database is secure. So strong password policy, daily updates and backups, access through firewall. We blocked about more than 10,000 IPs last year. Invalid and blacklisted emails are automatically blocked. Data transfers only to dedicated servers. The files are encrypted, and we only use supported operating systems. But I wanted to focus on the fact that there is actually a downside to locking health data. So using security and privacy as an excuse, I don't think is going to be acceptable in the next few years. And this is just highlighting why we need to understand better health and disease using the application of machine learning on health data. So this is a quote from Arnold Relman, who was an editor-in-chief of the New England Journal of Medicine. Many people think that doctors make their recommendations from a basis of scientific certainty, and the facts are very clear, and there's only one way to diagnose or treat an illness. In reality, that's not always the case. It's almost like it's never the case. Many things are a matter of conjecture, tradition, convenience, and habit. And I'm pretty sure people are familiar with Vinod Khosla, who is also a big proponent of trying to reduce the variation in care by looking at what the data is telling us. There was a study that was published by the Institute of Medicine in 2011, and they convened expert panels to look at more than 300 clinical practice guidelines that are being used in the United States. And their conclusion after looking at all these guidelines is that for many clinical domains, high quality evidence is lacking or even non-existent. And often providers rely on low quality evidence or expert opinion. So what I wanted to do now is to show the power of data. And I'm going to describe 2 projects that we were involved with using the Mimic database. The first one is trying to predict what happens to a patient in terms of very specific interventions. And for this project, we looked at data within a 6-hour period of time to see whether an intervention is going to be started, stopped, or continued 6 hours into the future within a 4-hour time frame. And we would move that time frame and see how good are we in terms of predicting the following interventions: mechanical ventilation, non-invasive ventilation, use of vasopressors, and fluids. And we use the long short-term memory networks as well as your convolutional neural networks. And we had, for the most part, so these are the outcomes that we wanted to predict, and those are the methodologies that we use. And for the most part, we had very good results. The AUCs would vary depending on what we were trying to predict, but it's a good proof of concept that you could predict interventions in the intensive care unit. And this may not be the most clinically relevant interventions to predict, but I could say that we could do this with initiation of renal replacement therapy, and that could have some implications in terms of staffing in the intensive care unit. But with the right granularity of data, you could do all these predictions of what's going to happen to the patient in terms of aggressive interventions. I also wanted to point out that you don't need fancy methodologies to be able to get some leverage out of the data. In this particular project, what we wanted to do was to provide some visualization to help us interpret laboratory results in intensive care unit. So the main motivation for this project is that when we order lab tests in the ICU, what the lab would give us would be a reference range. And do people know how they come up with the reference range? So they basically would survey about 200 healthy controls every couple of years, and whatever is the distribution of their lab test, that becomes the reference range that is given to us wherever we are, whether you're in the outpatient or in the ICU, you're given the same reference range, and that is based on 200 healthy volunteers. And our hypothesis is that that doesn't mean anything to us in the intensive care unit. So this reference range that's derived from 200 healthy volunteers are not relevant at all when we are taking care of patients in the intensive care unit. And then the critically low and high results that are being, again, given to the provider. So for example, you get an alert that the potassium is very high, that you have to act on it. Those results, those cutoffs are actually established by expert opinion, and they vary from hospital to hospital. And it's almost unnerving to think that we're doing that still in this age when we're surrounded by copious amounts of data, and we could actually relate a specific lab value to a specific outcome. So our question for this project is that, can we look at the distribution of laboratory values according to clinical outcome? And what we did was this. We looked at all the lab results in MIMIC, and then we, for the most part, we look at the distribution of two specific outcome groups. We divided the patients according to the worst outcome, which is death, and the best outcome, which would refer to the people who survive their ICU stay with the shortest length of stay. So we now have two groups, the worst outcome and the best outcome. And then we compare the distribution of their lab results with the reference range that's given to us. So here's an example of serum lactate, which is a lab test that we frequently order in the intensive care unit. And between these two lines, this dashed lines, the black ones would represent what the lab would give us as a reference range. And you could see the distribution of the people with the worst outcome. And that is the one in red. That is the distribution of serum lactate for people who died, while the blue represents the distribution of the people who survived and the shortest length of stay. And you could see here that even beyond the normal reference range that is given to us by the lab, there is so much overlap between the groups that had the best and the worst outcome. So which means that this reference range that is given to us by the laboratory, it doesn't really mean anything in the intensive care unit. Would it be great if the lab could actually give us the probability of an outcome based on a value that we're looking at now? And this is basically what we did here in this stacked area chart. For every lab value, we give the distribution of the worst and the best outcome group. And obviously, this is only based on a single lab value. In this case, we looked at the worst serum lactate of that patient and tried to provide that to the providers with a representation of the probability of a certain outcome. We think that this is the first step in developing a data-driven, outcome-based approach to interpreting laboratory data. And it really opens opportunities to develop more personalized ranges based on relevant clinical context. So some of the future directions of this project would include, now we are asking the MIMIC and the Philips database what levels of hypokalemia and hyperkalemia are truly associated with arrhythmias. Maybe we don't have to panic with a serum potassium of 5.5 in the ICU for your particular population. Is it the same across patient populations? Is the level of hypokalemia and hyperkalemia associated with arrhythmia different in the medical ICU compared to the coronary care ICU, compared to the cardiothoracic ICU? Our gut instinct would say that yes, it would probably be different according to the patient population that you're looking at. And does the risk of arrhythmia vary according to the phase of illness? Is it the same on post-op day number 1 after a CABG versus post-op day number 5? And chances are, again, the answer would be yes, it will be different. Is it different when the patient is just coming in with early phase of sepsis versus when a patient is already recovering from sepsis? So with that, I'd like to end my presentation and follow us on social media. Thank you.
Hello again. So this is a continuation of what I spoke on earlier. I think it's easy sometimes to talk about some of these technologies as if someone else is out there doing them. And I think in this case, it's interesting because in a matter of slides here, I think I can show you that it's become relatively easy to set up your own blockchain and build something on it. This is a very simple application that I built over the course of a couple hours. I'm not a career programmer, I'm a physician, and so the ability that we're reaching today where lay people such as ourselves can achieve some of these results, I think is very powerful and speaks to the massive open source movement that is going on. So I'm going to demonstrate the creation of a simple health app that stores on an active running private blockchain. So as we'd mentioned, blockchains are distributed, decentralized ledgers of information. I'm going to focus on the Ethereum virtual machine and the Ethereum blockchain. That, as I'd mentioned, is the second most well-known blockchain out there, and it enables us to do important things in healthcare like smart contracts. And again, these smart contracts are programs that you create. They're pushed out to the blockchain. They reside, are validated on the blockchain, and are run in a distributed manner. Ethereum does have multiple networks. While there's one main network, today you can take the source tree and run your own private networks without any cost. This application is very simple. It initializes a set of side effects, wheeze, cough, angina, vertigo, and then uses a web browser to go through a standard web server, and then you're able to use the web interface to increase the number of symptom counts that you might have in an arbitrary scenario. I'll show you the smart contract, which is actually very small. It's written in a language called Solidity. So I do show 2 or 3 slides with a little bit of code in it. I understand that many of you out there might not frequently dabble with computer programming. I think you should, but you don't need to for this. The purpose of this is to show you how small some of these things are and how much of the backbone is already there for us to use. The list on the left is the list of the files in the project, and that's it. Under the public tree there is just normal web files, HTML, some JavaScript, and CSS. There's a server file below that loads an express web server with 2 functions. That first function is increment, and then there's a second function, get. The first function increments the side effect. Okay, so that's how you count the side effects. And the get returns the total counts on the blockchain for each side effect. I'll very quickly show part of the smart contract. I think that for those people that do have some programming experience, you'll recognize that very quickly. It again has 2 methods, one to increment, account for a side effect, and another to return that from the blockchain. Deploy contract is interesting. That's run only once. When the blockchain is initialized, deploy contract pushes that smart contract out to the blockchain, and that's it. Okay. So this is a large part of the server file. It's starting up at the top. This is the function that increments, right? So part 2 uses the API to call a smart contract out on the blockchain and increment. The area 3 just goes back to the blockchain and says, give me back the number of side effects that are on that blockchain. This is the smart contract, and in fact, it's about 70% of the smart contract. It looks very similar to other things there. In part 2 here, we're just initializing a storage area for the list of side effects. Part 3 is the function that returns, again, from the smart contract, the total side effects for any, the total count of side effects for any side effect. And finally, the smart contract function that increments. There's really not that much here. Finally, this is the entirety of the file that deploys that smart contract out to the blockchain. It's only got a handful of lines. It's mostly just requiring files for that. Here is just how we start the blockchain. The blockchain started. You can see there's a number of different keys and signatures up there. Finally, down here at 2, we start the web server. And the first thing that happens is that there's this transaction, and that transaction is the smart contract being pushed out. Okay? This is how it looks like from the front end. It's a very simple web interface. It allows you to type in one of the side effects there, push a button, and another transaction happens, another block happens, and you're able to push that out there. So this is something, we speak a lot about the magic of all of these technologies, but this is something that you can largely explain in 10 slides. And that's something that's happened over the last year. This was so much more difficult to do last year. But today, non-career programmers, such as myself, yourself, can potentially start to at least explore these things. And that's it. Thank you.
Kevin, I just want to point out that it did not go unnoticed that one of your files was called sideeffects.sol.
That's Solidity is the name of the language, but yes, that's funny. I hadn't picked that up. Thank you.
All right. Can we get the questions coming up here? While those are loading, I actually had one more question for you. So in the blockchain, as you add the side effects, if you add a count of 1 to asthma, what is the overall kind of size and complexity increase that you get with the blockchain itself in terms of computational resources and whatnot?
Not very much in terms of computational resources. The block size is something that's determined independently and as part of the protocol, and that's something that there's a lot of discussion at Bitcoin at the moment by how big that they want that block size to be, and there's a number of different architectural considerations for that. For this, I don't know the size of these blocks, but I would imagine relatively small. That again is defined as part of the Ethereum API.
All right, Leo, I was interested in the normals don't count in the ICU. That's totally true. So we've got a question up here saying lab values are not independent from other variables, and how do you take into account the stratification of interactions and confounding from other factors?
So we did, and I think I mentioned that during my presentation, that clearly mortality is affected by not just one lab value, but it's more of a proof of concept. For certain outcomes, for example, arrhythmias, maybe there is also interaction between serum potassium, serum magnesium, but again, to us, this is just the first step. This is not something that we would already implement next week. We would like to recruit other brilliant minds to join us in these efforts in trying to make the lab results reporting much more relevant to the clinicians who are looking at the lab results. We still think that this is better than giving us a reference range based on healthy volunteers.
Agreed. Kevin, do you have any comment
Yeah.
on that?
In terms of these?
Well, you can answer one of those, but actually, I mean, you're a clinician as well. What about the normal and the recognition that, you know, what's posted as a normal value may not be? Fair enough.
Yeah, I think you always need to be very careful of the data, and if there's a concern in the quality of the purity of the data, that's something that has to be taken into account. These are systems, after all, and systems that are controlled by us.
All right.
There are a number of, I think, very good questions that are coming up. One that I've seen twice now is that the Bitcoin was recently hacked, and I think another question up there earlier had mentioned about 30 million. These are as secure as the cryptographic protocols that protect them. And I'm not familiar with the circumstances behind the most recent hack. It may have been possibly the leakage of someone's keys. But 30 million to me seems relatively small, and I'll explain that. As of a week ago, when Bitcoin was $13,000 a Bitcoin US, the market cap was $214 billion US dollars in the Bitcoin. And that is effectively a bounty. It's a bounty testing people to go out there and try and break that. So to me, a $30 million slip somewhere, which could be from some other reason, doesn't necessarily mean that it was entirely hacked. There was something else about hosting blockchains locally and forking blockchains. Blockchains can be forked. There have been a number of notable instances where popular blockchains have been forked. That doesn't invalidate the encryption. The data is still encrypted. It just bifurcates the source. And then there's a whole complicated protocol of sort of what happens with the miners and so forth. These are obviously active, very active areas of research.
There's a couple of questions up here about corrections. You know, if an erroneous
Yes.
entry is made, talk to us about that a little bit.
Yeah, so that's something, you can't go back and change that data. When I showed you the picture earlier of the Merkle trees, the thing that I had to gloss over for the sake of time is that the moment you change some data, you're affecting the cryptographic signatures of everything after that. So the color was changed in one of those boxes, and it changes the color down below that. You can't do that. You have to accept that the data is there permanently. You can amend the data. Right? So there's nothing to say that you post something there and a week later you find that the value needs to be updated. You amend that data and then from that stage forward the data is ostensibly correct. But it doesn't hide that sort of that state that occurred beforehand and that will always be there. I think in many cases as a source of good, I think. You can amend it, you're just adding, re-amending the data differently later on.
I had a couple of just random comments. Leo, the shirt that you wore last year, where's that cool shirt?
No, there was a question about the identification that you might want to comment on. Is it really possible to de-identify health data?
So that's a good point. I'd actually kind of like to hear your comment on that as well. I mean, you've got the Mimic database, which is actual live data that's out there. It's not like you can just go download a copy. You've got to, ask permission for it. But it's data, it's real data. Yeah, if somebody's got a patient's healthcare record in front of them, and then they've got a whole bunch of data that's in a de-identified database, you can certainly go back and do kind of nearest neighbor matching and find somebody's data in there. So yeah, there's no such thing as totally de-identified data if you've got the key to that data. But for all intents and purposes, I mean, if you've got a database with 1 million interesting facts in it on a different set of patients, where's the value in that? Who's going to be looking for your specific information? It's effectively de-identified.
So, I mean, it depends on the data. So definitely structured data would be easier to de-identify. The free text notes are, I would say, much more difficult to de-identify. Say, for example, we had intentionally removed the data of the Boston Marathon bomber because if you type Boston Marathon bombing suspect, it will show up. And it wasn't identified as a protected health information using the algorithm that we have. So unstructured data is easier to re-identify. Images, I think the jury is still out. We have some concerns about releasing CAT scans, so cross-sectional views of the head, because they say that you could actually reconfigure the face based on the CAT scan. But I still would like to actually do that as an experiment. I would like to look for a CAT scan and see what is the face that I could put together based on the CAT scan, and does it really look similar to the original person? But I agree with you. If there are 10 million patients in the database, it's going to be much, much harder to look for a specific patient.
Okay. All right. Is DNA data de-identifiable? Ooh, that's a big one. Probably not. I guess
well, you could hash it.
Okay.
You'd sort of lose that.
Yeah. I would argue that if you've got somebody's actual genetic code, though, and we ever get to the ability where we can have, exact understanding about how that all interrelates, even at kind of the, the methylation and kind of the non-genetic aspects of it, that would be a interesting thing to try to do.
I want that question, what's the best and least time-consuming way of learning about blockchain? Any advice to people who wanted to go into this field?
Yeah, there's lots of different sources out there now. For those that are more technically inclined, there's a brilliant book on Bitcoin by someone at O'Reilly. But there's also other books out there, and I can, if you email me, I'll remember the names later, that explain it at a sort of a different level, at a much more lay level, if that's your interest. The other way is to go out. You don't have to buy an entire Bitcoin. You can go out and you can get a wallet and play around a little bit with some money here or there, and participate. So it's wonderfully open in that regard. There's a load of resources out there on the internet. If you search, you'll find loads of these, and many of them have wonderful degrees of information. So it's really just a matter of sitting down at a computer and spending some time on Google.
All right, I think we've got one more question. Who would be responsible for storing a patient's private key, and how would that be managed?
Yeah, so that's one of the critiques or questions that a lot of people have. For people that are interested, if I had my healthcare data on a blockchain, I could control my own private key. There are Bitcoin exchanges, Coinbase and so forth, where those people don't necessarily want to control their own private keys. You're ceding some of that control to the exchange, but for those people that don't want to be as involved, it's their choice though. It's their choice to say, I want you to be the representative of me out there. And if you do something that I dislike, I and populations like me can move to a different one, or I can keep that data myself.
There's a service for everything. All right, with that, I think we'll close it off. Thank you all for coming. Anthony?
Thank you. I think we'll take a nice 20, 25-minute break, and we'll reconvene after that. Thank you.